so we're looking at dealing with charges. And if I have two charges, and we're looking at a vector quantity, we have forces. We have the electric force between two charges, and the formula K sub C Q1, Q2 over R squared. This is the force on one from two, R to that. There. We have units of newtons, or SI unit, I should say, is the newton. The fact that the unit of force is a newton, I'm hoping it's not a shock to any of you. If I have only one charge, and I'm talking about the whole electric phenomenon, we have the electric field. And the electric field from a charge is just basically the force divided by a charge. So the Coulomb's constant times the charge over R squared, R hat. Now I do need the subscript here because I deal with two charges and I have to give which one's the point of reference. Here I don't need a subscript because I have only one charge and that's the point of reference. If I'm dealing with a scalar and I have two charges, well, I've got an energy to deal with, so I have my electric potential energy, which is K sub C, Q1, Q2 over R, and then officially plus some constant. And so as not to confuse it with the Coulomb, got to do the unit. The SI unit of the electric field is, please, someone share with me. Say it again? Yes. Ooh, something else I'm going to put on the chart there. I will get hearing aids on the 10th, and I will be able to hear the whispers from students. Yeah, I'm
We'll be
looking forward to
even
hearing.
quieter.
Pardon?
We'll be even quieter.
That's quite possible. There's only so much I can turn it off, I think. But I did hear some sounds yesterday when I went in for the consultation that I don't think I've heard before. So it was exciting. So until then, speak loudly, boldly, like you are correct and everyone else is wrong.
Sounds about right.
All right, so we obviously in my chart here, we've got this gap. Oh, and once again, I forgot the units. What are the SI units of electric potential energy? Boldly, loudly.
Newton meters or joules?
Yes. Let's go for the shorthand, Joule. The plus a constant. Why plus a constant? What does that allow us to do? And once again, I'm overwhelmed with the impact that I had on almost all of you. If I asked you what's the potential energy of a system, what's the easy answer? without any additional information. I feel like one of you has input of the answer. He's just too shy to say it. I'll leave that as a mystery then. All right, so if I have, so when I went from when I went from force to electric field, I got rid of one of the charges. I technically divided by it. Over here, the electric field is equal to the force on 1 from 2 divided by the charge of 1. That would be the electric field from 2. So surely there is what we could do here is we could take our potential energy formula here and just divide out one of the charges, and that's got to be something. So let's just do it. So if I just take my potential energy times the charge, divide by one of those two charges over R, I feel like that should be something. What would the units be?
Joules per coulomb? Is it joules per coulomb?
Don't ask, just tell me.
Joules per coulomb.
Yes. Next time, pound your desk a little bit harder.
Okay.
All right, it is indeed a joule per coulomb. God, that is so much to write. Newtons per coulomb I can handle, but joules per coulomb, really? You expect me to write all of that? So let's see if we can come up with a one word for that. How about a volt? Now we get into just fun vocabulary stuff. The unit of this is indeed a volt. The symbol for it is a capital V. Another one of those situations where if I wrote those two V's do not mean the same thing. This is the quantity, this is the unit. It is unfortunate, but it is just the way it is. Now, I have not described voltage. Yes, I realize the word volt we have just mentioned, but voltage is coming up. It is related to this, but it is not this. This V on the left here, this V right here is known as electric potential. This is electric potential energy. This is electric potential. Electric potential. So if I ask you what is the potential, given the context, electrical, if I ask you what's the potential, this is the one I'm asking for. If I want this one, I do need to use the word energy. This is potential energy, this is potential. Still have not talked about voltage yet. So first off, if I've got a, let's see, multiplying times K. So let's make this a 4 nanocoulomb charge right there. If I am 1 meter away, what is the electric potential? Now, you might have noticed that there is an issue here. Plus a constant. Not the same constant as that one, necessarily, but a constant. Actually, units would be different, so they wouldn't be the same constant. All right, so what's the potential at this point? Potentially, it's just a simple plug and chug. One meter away. Assume spherical symmetry, and since it's spherical symmetry on the charge distribution, I can assume it's a point charge at the center. Nano 10 to the negative ninth.
Thank you.
Who's not? That way the numbers work out much nicer than I said. What'd you get?
What the? Joule, volts. I don't know if that makes any sense.
So I got 36 volts over here. You did ask another question that I ignored. And I'm gonna come back to it. Anyone else get the same thing Laura got?
36?
That's the same numerical answer.
Yes, same numerical.
And if you multiplied, if you did plug and chug, you would get 36, which is why I chose 4 nanocoulomb, so it would work out. However, Laura did say something else that Luis did not say.
The units, volts.
Yeah, okay, there we go. All right, so 36 volts. Anyone dissatisfied with that answer? If Luis is speaking for everybody, no one's dissatisfied? Oh, Laura?
I am dissatisfied because I don't know what the constant is.
Huh, okay, so what is that constant? If the formula you're plugging into, if I want to know the potential at that point, and that's equal to V is equal to KQ over R plus some constant. Just trying to differentiate it from the other one. Let's see, that'd be 9 times 10 to the 9th, times 4 times 10 to the negative 9th, divided by 1 plus C2, and I get 36 plus C2. What do you want the constant to be? All right, Stephanie? Do you want to actually, you don't want to say it? This gave me a hand gesture. So, if the constant is 0, what's the potential at this point?
Joules per coulomb per volts.
Okay, so if the constant is 0, that is 36 volts. Suppose the constant is 10. Okay? How do you decide what the constant is? What decides? Who decides?
You,
Me.
the individual.
Thank you.
Because it's like potential.
Well, this is potential. I mean,
Exactly.
potential
The
energy.
other one. That's
The
what
empty
I
one.
said.
Yeah.
Just continue.
If the constant were negative 36, what's the potential here?
0.
Yeah. So what the constant allows us to do is pick 0 wherever we want it to be. Now, traditionally, you can say the potential is equal to 0 volts at R is equal to infinity. That's the traditional. If you want the constant to, if you want to ignore the constant, just say the potential is 0 and R is equal to infinity. And sometimes in problems I will do that. But if I don't do that and I ask you what's the potential here, the easy answer is 0 volts. Because I said so, or because you said so. However, let's go ahead and stick with this for right now. If that is, there was a problem years ago that I asked, and I set up the problem, gave the distribution, gave spherical symmetry to the distribution of charge, so that you could assume that the potential was 0, that the charge was a point charge at the middle of the sphere. And I made the comment that the potential at the surface is, and I made up some number, volts. How can this be? Everyone missed it. I was disappointed. You can make 0 wherever you want it to be. I mean, they were so used to the brainwashed of this that they missed the easy solution. The surface, it was 500 volts because I said so. Or because someone said so. Anyway, all right, so but given this, if we assume that, that means that the constant is going to be 0, because if R is equal to infinity, this is close enough to 0, and so the potential is equal to whatever that constant is. And so if I'm saying it's 0 and R is equal to infinity, if volt potential is 0, R is equal to infinity, then the constant has to be 0. All right, now if I'm next going out another meter, what's the potential there? Assuming this. Pardon?
It's half of that.
Okay.
It's 18 volts.
And I've got another meter.
No way, wise.
12. 12.
I think you said 12
Yes.
volts. Don't forget units. We are not savages.
True.
I think anthropologists will tell you that what separates savages from civilized man is
Units.
units of measure.
Of course.
I haven't confirmed that, but I'm just assuming it's true. We'll go one more and then we'll stop.
9 volts.
All right. And obviously, it'll get smaller and smaller and smaller. I hope it's obvious. Now, recognize also that if I have a universe here and I have just a single charge, that's 36 volts 1 meter away everywhere around here. It doesn't have to necessarily be to the right. So there's this line. There's a circle, actually 3-dimensional. It's a sphere of surface where everything is going to be 36 volts. There's another one farther out that's 18. This line right here, where everything is 36 volts, is known as an equipotential line. Pardon?
Why?
Equi, meaning equal, potential. Everything along this line is the same potential.
So all of the spheres would also be equipotential?
Yeah, there's a whole bunch of them. There's equipotential surface here, different equipotential surface here, different one there, and so on. if we look at the electric field, actually, let me ask you, what do we know about the electric field from a positive charge? Okay. And fine. I have one doing this and one doing that.
Has to be outward.
Out, yes. My electric field goes outwards. And as it turned, in this particular case, I think it's a little clearer than in some bizarre shape, but at the equipotential surface, the electric field is perpendicular. So, assuming electrostatic equilibrium, the electric field is perpendicular to the equipotential line. Or equipotential line, surface, however many dimensions you're doing. So if I have a solid, that is charged and in electrostatic equilibrium. We talked about before that the electric field is perpendicular to the surface. Well, adding to that, the surface would have to be an equipotential surface. So if I took wherever my cube is, well, I'll take a cylinder. If I took the cylinder, added charge to it, backed off, so that it could get into equilibrium, then the whole surface of the cylinder would be the same potential, the electric potential. Questions here? I'm going to write something else up that is beyond the scope of the course, but just in case you happen to run across it. The shorthand notation for this